Welcome to our lesson about solubility. We're going to start with a bunch of key terms to make sure we're all on the same page. You've heard about precipitation, rain, snow, sleet, hail, anything that is coming down. In chemistry, that is when the solid ends up collecting at the bottom. It's your precipitate. Whereas on the right side, the same sodium hydroxide is in solution. It's been dissolved in the water. Okay, and this can also be called a homogeneous mixture, like homogenized milk. We don't have the fats separated out. It is all in one solution. So again, solute, that is what is being dissolved. Solvent is what is doing the dissolving. And this again is the universal solvent of water. We're going to be using that a lot. And this is not a chemical reaction, even though it has the chemical equation here. It's just saying, then we put the solute and the solvent together, we get our nice solution. Now, we have a small amount of sugar on the left, a large amount on the right, so we're increasing our concentration. So as we go to the right, we're increasing our concentration. If we're going to the left, we're decreasing our concentration and we're making the item more dilute. These actually have specific points that we can discuss. When it's in that dilute stage, it's unsaturated. There is more sugar that I can put in my super extra large thing of coffee. There's still more room to add some more sugar to dissolve. In the saturated state, I have the maximum amount of sugar dissolved. So if you're seeing this in real life, it's when you're stirring and you're doing what you can right in that situation to get all the interactions and the sugars dissolving, but maybe a couple little crystals are just seen at the bottom. That's pretty close to your saturation point. Super saturated, you do this all the time if you're trying to make some iced tea sweeter because it's so cold, it is not going to dissolve a lot of sugar, so you end up with a big clump of sugar at the bottom. The cool thing about super saturated is if you're doing that under the right conditions, you are going to get crystalline. So if you ever see anything about crystalline structure in terms of talking about saturation, you can think about there was too much solute for the solvent and it crystallized. Here we go with a little pictorial view chemistry wise. What am I looking at here? So on this left side, I have a structure of silver chloride. So we have the silver cations, the chlorine anions, they're all being attracted together with that ionic bond. It's sitting there pretty much in its solid form, as shown by the S here, okay? And so that means that is if the precipitate is sitting at the bottom. So if we're looking at this arrow here, that's going to the left, we are creating that precipitation when we're going that direction. How about if we are going to the right? We're on the dissolution part. We're taking the solid silver chloride and breaking it down into its ions. And that's what the picture is showing. This is the start of the dissolving process. We still have the cations and anions. Okay, so we're still up conservation of mass. We're not taking anything out of the beaker. Same amount of silver ions, same amount of chlorine ions, but the water is getting pushy and going in between and pushing it out so there's separation. This is not a covalent bond. We're not breaking the bond. This is an ionic bond in this case, and we're just stuffing some waters in the way, but there is still attraction between the positive and the negative particles. Okay. And what's another thing that people get confused on? This chlorine is in its ion state. It's an anion. It's in the water. It's already matched up with the silver. So this is not its gas stage. So you don't worry about Brinkelhoff's when you are putting him into its solution stage. And that's what that AQ stands for right there, aqueous. And that's just meaning dissolved in water. So left picture, precipitate. Right picture, we are starting to go into solution. We're starting to dissolve. But we still have all those items right there. Okay, so how can we increase the speed? I talked about it a little bit. We can stir it, and then we have more access to all the different surface area sides of that solute. The other thing is increasing that temperature often is going to help. Hot tea, you can have more sugar be dissolved than cold tea. Okay, and this amount that can be dissolved is determining our solubility. The maximum amount of solute that will dissolve in a given amount of solvent. Okay, so this one has the solvent of water. Again, we're putting everything in 100 grams of water. You're going to read the y-axis to find the solubility and the x-axis to find the temperature. So let's try some problems with this graph. What is the solubility of sodium nitrate at 75 degrees? So we have all the chemical formulas on the left side, so we better figure out the chemical formula. Sodium is an anion with a +1 charge, and nitrate is an anion with a minus charge. They are perfectly matched together, so I don't need to do a crisscross. I just got to find sodium nitrate right here. And then here is its graph. And we're going to be looking at this line on the graph for finding our answers for this first one. What is the solubility? So that's what's on the y-axis. We're going to find what the matching y-axis is for the intersection of the temperature and our curve. What temperature? 75. All right, well, I was going on well until I got down here. There's no 75. Yep, you're going to have to interpolate where that is going to be. You might have to use algebra and actually find the exact point where 75 is. This is an SOL. Look at the answers. If all the answers are really close together, you're going to have to do a little bit more accurate estimating. But if the answers are way far apart, then you know, okay, I can just guess. Between 60 and 80, halfway in between is 70. And then halfway in between 70 and 80 is 75. So I'm going to estimate that 75 is right there. And I'm going to use a ruler and draw a line directly up. That intersection of the curve and the 75-degree line is the solubility point. That is where it's saturated. We have the most solute in that 100 grams of water. So now I'm going to go to the left with my line. And again, I'm going to estimate that it's like 142 or something. Again, you might have to do more accurate guessing, but sometimes they just give you 200, 280, 70, and 140, and then you're going to go with what's closest. So even if you're like, oh, I think it's a little bit higher than that, it's multiple choice. Pick the close one. Okay. What if I had 200 grams of water? So if I can get 142 grams out of 100 grams of water, because the graph is giving you 100 grams. If you had 200 grams of water, what's the difference here? Multiply by 2. So 284 grams can be dissolved in 200 grams of water at 75 degrees for sodium nitrate, only sodium nitrate. Okay. Now here one goes the other way. What temperature? So temperature is on my x-axis. So I'm going to have to drop down to find the temperature. Can 100 grams of potassium bromide be dissolved? Potassium, that's K. Bromine, Br, KBr. So that is this graph right here. But this time we are using 100 grams of potassium bromide. So we're finding the 100. And we're going to draw a line from the 100 to where it intersects with this graph. And that is putting us right about here. And I'm going to drop down a line on the intersection. That is the saturation at 100 grams is, and that looks like right in the middle. So I'm going to say 90 degrees. So at 90 degrees C, potassium bromide can dissolve 100 grams in 100 grams of water. So that's pretty even of solute and solvent mix. Oftentimes, if you have to guess, you're going to guess that the solute is less, but that's not always the case. As you can see from this graph over here, some of these things we can get at 70 degrees, we're getting like 300 grams of sugar in 100 grams of water. Sugar is still the solute here. Everybody on this curve is the solute. Okay, as you notice, these guys all are increasing as we go to the right. What's going on when we go to the right? When we go to the right, we're increasing the temperature. So as we increase the temperature, we are increasing solubility because we're having that general positive slope there. For these substances, as we increase temperature, we're increasing solubility. There's somebody here that's not agreeing with that. That is cesium sulfate. Cesium sulfate. Okay, no prefixes because it is a cation and an anion when we're naming him. So he is not increasing with increasing temperature. His solubility is decreasing or going down with increasing temperature. Okay, and now let's go over to something else that tends to have a negative slope on the graphs, and that is when we're looking at what's in soda to make it flat. So a flat soda has less bubbles, so it has less carbon dioxide dissolved. That happens for two reasons. One, when it's in its little can or bottle here, it's pressurized. So that's helping hold all those dissolved carbon dioxide in solution in the soda or in the water, because it is primarily water. Now, when you open it up and sit it out, then some of those bubbles are going to be leaving because it's not pressurized anymore. It's not sealed anymore. But there's another reason why it gets flat, and that's when it gets warm. We just said if we increase the temperature, we can get more sugar to be dissolved. That's absolutely right. The soda is not the right way. As we increase the temperature, our soda gets more flat, so less is dissolved. Gas solubility is backwards. That's our little hypothesis that we're going with. That carbon dioxide works differently. So as we decrease the temperature, the soda can dissolve more. As we decrease the temperature, as we make it colder, the soda can dissolve more. Its solubility in water graph would have a negative slope. So if we look over here, look at all these negative slopes. So when we measured all these things, they tended to have those negative leaning slopes. As the temperature got hotter, the solubility went down instead of up. Gases tend to dissolve better when it's cold. And so this graph is that data to back up our hypothesis. So let's use this graph to answer some question. What is the solubility with units 10 to the -3 moles per liter? So it's just saying you can read directly off the graph because we're going to match those conditions of carbon monoxide at 20 degrees. 20 degrees right there on that line. I'm going to go straight up. Which intersection am I going for? Carbon monoxide. CO, mon means one oxygen. Okay. And so that would be this graph. And we're going to go over to the left this time. So we're not dropping down, or so we're going up and then to the left. And that's our solubility of 1.0. Don't have to do anything else to that because they wanted the units to stay what the graph was. At 20 degrees, that intersection with the carbon monoxide graph is a 1. Okay, what is the solubility, including units, of oxygen gas at 20 degrees? So we have that line that was still right there. So let me just erase this other part. And where are we going this time? Oxygen gas, O2, Brinkelhoff. It has 2 oxygens to make that oxygen gas, not just 1. We're going over to the left. Again, if they ask you to do a very specific analysis, yes, you can go through and do that using a scale to get the answer. For now, we're just going to kind of give an estimate, probably about 1.4. 1.4 times 10 to the negative 3 moles per liter. That's how those units are. This moles does not have a superscript, so it's like how it's written. The liters, though, has a -1, which just means it's on the denominator. So if we had to put this out in expanded form, we know that this is a really small number because it's a negative. So we need to go 3 hops to the left, 2, 3. And that is where our new decimal place is, 0.0014. So they could give it to you with expanded notation on the graph. And so then you would know that is the molars that would be written there. What's next? What if a number is not on the line? All right, so let's just randomly pick a number right here. Okay. If it's above the line, it's supersaturated. So this spot, which is somewhere around 14 degrees C and maybe 1.3 solubility, that is above the carbon monoxide line. So we have too much solute for that temperature because we're up here and their solubility is down here more like 1.1. We have too much solute to dissolve. So if it's above the line, it's supersaturated. So this guy is above the line for carbon monoxide, nitrogen gas, and helium gas, but it's below the line for oxygen gas and for methane gas. So oxygen can handle something like 1.5. So he's like 1.3, oh, that's no big deal. I can easily dissolve 1.3 because that's less solute than what I can handle. So if it is below the line, it is unsaturated. So methane and oxygen, when I'm looking at this point, are going to be unsaturated because they could still dissolve more at that point. So make sure when you're talking about what the line is, look at the particular one. Helium has way down here, its solubility is low. Okay. So most of the time, if I'm putting in numbers on this chart, helium is going to be supersaturated because any of these points that I plot, so if it asks you to plot a point, plot the point. If you are above your gases line, supersaturated. On the line, saturated. Below the line, unsaturated. Okay, so compare the solubilities. When a species is 15 degrees, so that's halfway between the 10 and the 20, and at 1. So here is our point to compare. So helium is in what? Supersaturated, because helium was only going to dissolve about 0.4 at this point. And they want us to dissolve 1. It can't get there. There's too much. Supersaturated. Nitrogen gas, supersaturated. Carbon monoxide can dissolve about 1.1. So carbon monoxide can dissolve more. Okay, so carbon monoxide is unsaturated currently because our point is below the line. Oxygen and methane are unsaturated at that point. And that's all for today.